PDEs. Are there questions so far?
I have a question. Um,
Yes.
so I think this example you've written here, it kind of sounds like that's a discrete Fourier transform. I assume you would have like a finite number of data points of the signal. What's the relationship between the Fourier transform and the discrete Fourier transform?
Yeah. So the discrete Fourier transform is going to just sort of be it's going to be like a Riemann sum. It's going to be a sum instead of an integral in this case, right? Because you're not going to have values of f at all values of x in this case. But the discrete, the DFT in the limit, as you take the mesh size to be small, you will recover the continuous Fourier transform. So
Mm, So
yeah,
if
so
you,
you can do a number of things to handle that with data. You can sort of smooth or interpolate your data to get a function, um, and then compute this, or you can just directly compute a discrete Fourier transform, which would be, yeah, it's the sum approximation of the continuous.
so it sounds like, is this over a finite domain then? Do we have Fourier transforms over finite domains as well as over the real line?
Uh, yeah, right. So, right, that's a good point. So essentially, in that case, you can, yeah, you can truncate these, um, you can truncate these integrals, sort of in the same way that you would um, here, right, in order to get 2 pi periodic functions. So yeah, there you're you're sort of acting as if you have like an L pi periodic function, but just where L is going to be very long in this case. So so in the case of periodic functions, right, you can just say, well, if I periodically extend this function, then I have this function defined on minus infinity to infinity, and I'm going to Fourier transform that function now. Um, the thing that's convenient about periodically extending and then acting on unbounded domains is that usually it's easier to get kind of analytic formulas on unbounded domains than it is on bounded domains. So yeah, you're right. I mean, I sort of with that example, I'm going back to a case where you would sort of act as if you have a periodic function, or you can think of it as taking a function that's defined on a finite domain and periodically extending it from minus infinity to infinity. All right. Any other questions or comments? Okay. So yeah, so for what we'll do, typically you're going to act as if you're Fourier transforming over minus infinity to infinity. Um, if we if we look at an example, so let's take the following example. Let's say that we want to compute the Fourier transform of f of x equals some top hat function. So this will be a function that's 1 when x is less than a, and it'll be 0 when x is greater than a. And right at the point x equals a, it doesn't matter because there's not sort of a unique Fourier transform depending on what x is right at a there. Okay, so well, just for complete, let's say that it's 0 right at x equals a. Okay, so the Fourier transform, right, is just going to be f of k now is equal to the integral from minus infinity to infinity of f of x e to the minus I kx dx. Okay, but because this thing is 1 for x is less than a and 0 for x is greater than equal to a, this will just be an integral from minus a to a of e to the minus I kx dx, okay? And so if I take this integral, right, then I'm going to get minus 1 over ik, right, e to the minus I ka minus e to the I ka, or in other words, write that down here, 2 over k sine of k a, okay? So that's the Fourier transform. So I took f of x, right, which is this top hat function, right? And I Fourier transformed it to the function sine of ka. Okay, so as I for a fixed a, right, as I vary k, then my function sine of ka is going to look like this. Okay. So the interesting thing is that for this top hat function, right, I have, you know, low frequency modes that are represented. I have high frequency modes. I have this weird sort of, you know, alternation in the modes that are representative because there's not really any intrinsic frequency to this function because it's 1 here and it's, you know, 0 outside of some region. It has compact support.
Professor?
Can f hat of k be even? Sine of
Sorry?
ka over k. F
What?
hat of k should be even.
F hat of k should be even?
Because it's sine of ka over k.
Oh, yeah, you're right. Yeah, sorry. I misdrew that. Yeah. Right. So sine of k, yeah, that's right. So it's going to be switched. And in fact, it's going to have really yeah, that's right. It's going to be, that's right. It's gonna dwindle down as k goes out to positive and negative infinity. Yeah. So you're representing low frequencies and then higher frequencies, but the amount of representation that you get in frequencies is going to drop off as k shoots off to infinity.
Should it at 0 have like a maximum? Shouldn't it be like a because of L'Hopital's?
Yeah, you're right. Yeah, I probably shouldn't do this on the fly. All right. Yeah, right. So yeah, right. The limit as what k goes to 0 from above of sine of ka over k is going to be equal to a, right, cosine of ka. So it'll be 2a, right? And then as you move away, it'll drop off. Yeah, right. Okay, sorry about that. All right, so this is f hat as a function of k. Okay.
Professor?
Yes.
What suddenly became easier by transforming this into the frequency space?
I'm just demonstrating how to take a Fourier transform. Yeah, it's not, we're not trying to do anything other than, yeah, just show how to compute a Fourier transform integral. Yeah.
Yeah, I was thinking of its application. Like you said, it becomes easier to compute certain quantities in this new space, right? So what's that specific quantity?
I'm just demonstrating how a Fourier transform works in this example. Yeah, it's not, I'm not showing how anything's easier in this case. Yeah, I'll get to that in a minute.
Sure.
Okay. So so yeah, so then if I want to recover f of x from this, right, I can compute the inverse Fourier transform now, okay, which is going to be 2 over pi integral from minus infinity to infinity, e to the I k x over a, e to the plus I k x minus a divided by k dk, okay? And for that, we would need some complex analysis. Okay, so I won't go through that for now. Okay. Now let me get to a more concrete example, right, where we're doing this for differential equations. Okay, so let's say that we want to use Fourier transforms for differential equations. Okay, what do we want to do? Essentially, we want to do a number of things, right? So the step-by-step process is, first, we want to Fourier transform the PDE, okay, or it could be ODE, and initial conditions, okay. Then you solve in the transformed space, okay. And then lastly, invert the Fourier transform to get a solution in original variables, okay. So let's take an example like, let's say that we had the transport equation, okay, where we just have u sub t plus ux is equal to 0, and u of x0 is equal to some function f of x in this case, okay? Now we've already worked out the solution to the transport equation before, but let's do it using Fourier transforms, or let's at least see what that process would look like in the case of Fourier transforms, okay? So the first step is to Fourier transform the entire PDE. So if I take my PDE and I compute the Fourier transform, that would be the integral from minus infinity to infinity of ux e to the minus ikx dx, okay, plus the integral from minus infinity to infinity of u sub x xt e to the minus I kx dx, okay, equals 0, okay, because the integral of the right-hand side is just going to be 0, okay. I can notice, first of all, that if I define u hat of kt is equal to the integral from minus infinity to infinity of u against e to the I kx dx, okay, then this is going to imply that u hat sub t of kt is just equal to the integral from minus infinity to infinity of u sub t xt e to the minus I kx dx, right? So this thing here, right, is just going to be u hat of t, right? It's just the Fourier transform of the, or it's the derivative, the time derivative of the Fourier transform of u is the same as the Fourier transform of the time derivative of u, okay? You know, assuming appropriate continuity and boundaries, okay? What about this, right? What happens to a derivative when I Fourier transform it, okay? Well, I can figure that out just using integration by parts, right? So if I use integration by parts, okay, I can convert this into, you know, some scaling of the, I can convert this into some scaling of the Fourier transform of u by some function of k. Okay, so if I compute the integral from minus infinity to infinity of u sub x xt e to the minus I kx dx, okay, and I use integration by parts, then I get u e to the minus I kx evaluated between x equals minus infinity and infinity, okay? If I assume u goes to 0 for x goes to plus or minus infinity, then this will vanish, okay? And in addition, I'm going to subtract off the derivative of this term here, the antiderivative of this term here integrated, okay? So I get a plus ik, the integral from minus infinity to infinity, u of xt e to the minus I kx dx. So what is this? Yes, go ahead.
So if u goes to infinity as x goes to infinity, the Fourier transform of u also goes to 0 as x goes to plus minus infinity, right? That means the frequencies fade as k increases. Does it?
If u goes to 0 as x goes to infinity, or
yeah. Can we say that the Fourier transform also goes to 0 for higher frequencies?
No, I mean, not necessarily, right? Because you can have a delta. I mean, a delta distribution has a very high frequency. I mean, so you could have very high frequencies represented in a function that also has compact support, right? You could have infinitely high frequencies represented just over a region of compact support, right?
Yeah.
I think it's that the low frequencies have to vanish if you have a function with compact support, because you can't have a function that has arbitrary width. Yeah, I don't know that you can necessarily draw conclusions about the Fourier transform of a function based on the fact that it tends to 0 as x goes to infinity.
But I think knowing that the inverse Fourier transform exists should say something about it being like absolutely integrable.
Right. Yeah. But that's different from the
that sounds to me like it would have to have like vanishing tails. But I mean, we're talking about like integrating against delta functions and stuff, so I don't know how much of my analysis actually holds up here.
Yeah. Yeah, I'm not sure about that for now. Okay, so all right, so where are we with this problem? So essentially what we've done then is that by Fourier transforming, we've converted it to u hat t plus I k u hat is equal to 0. We've converted it to essentially an ordinary differential equation with this scaling in k that shows up, right? So now we know that if we also convert this initial condition here, we'll get u hat k0 is equal to just f hat of k. Okay, that's just the Fourier transform of the left-hand side and the Fourier transform of the right-hand side of the initial value condition. Okay, the initial condition. Okay, so now how do we solve this? Well, we just use principles of linear ordinary differential equations, and we end up with u hat k of t is equal to a of k e to the minus I k t in this case, right? Because if I differentiate this, then I'll get a cancellation there. This now is going to particularly tell me that this should be f hat k of e to the minus I k t. Okay, so what is step 2 now, right? Has been solved, right? We've essentially found the solution in the transformed space. Okay, so now we have to do step 3, which is invert this to get our solution back. Okay, and you can always sort of convert, try and compute these integrals by hand, right? But the advantage of Fourier transforms typically is that you're just you're going to have a lookup table where essentially you can figure out how to convert this back to functions in the x domain, right? So what is u xt in this case? U of xt is going to be 1 over 2 pi times the integral from minus infinity to infinity of f hat k e to the minus I kt dk. Okay, and if you work out what this is, anytime there's sorry, I left out the inverting part. E to the I k x minus t dk here. Okay, so anytime there's a shift in here by of the complex exponential, that appears as a shift in the function that you're inverse transforming back to, right? So notice this x minus t here, the shifting here. Okay, you can show that essentially this should show up just as a shift in f of x minus t. So converting back, we just get f shifted by minus t, right? And there's a number of ways to show that. You can use changes of variables or something like that. And so this is recovering essentially the standard solution to the transport equation. Okay, so again, 3 steps: Fourier transforming the PDE to start with, solving the resulting ODE in the Fourier transforming space, and then using inverse Fourier transforms to get back to the original space, the original X space. Okay, and so on your homework, you'll have a chance to, on the next homework 4, you'll have a chance to look at this in the